Morning, everyone. Hello. So today we're going to have some fun coding. Okay, great. So I uploaded in the Google Drive the handouts for today. Do you know where to look for them? Yeah. Okay, so let's try and see whether you find them. So the way we usually structure the lab is that we give out handouts in PDF. There's going to be 3 versions depending on which programming language you want to use, whether it's Python, MATLAB, or R. There are all of those 3 versions you can choose. There's going to be some assignments. I'm going to go through them, explain a little bit of the reasoning behind it. Essentially, I'm going to give you some snippets, but you're going to be writing most of the code. This is how we do it. And of course, if you have questions, both on the theoretical and on the computational part, feel free to ask. And these PDFs do not include the solutions. What I usually do personally is that I start the lab without the solution, and you try and you start, and then usually midway through the lab I actually release the solution, because I found releasing the solution beforehand is not good, because then you are tempted to basically copy paste code, and these are 2 drawbacks. The first drawback is that you don't learn too much out of it. The second drawback is that you are done with the lab in 10 minutes and then don't have anything to do for the rest of the next 1 hour and 20. On the other hand, releasing the solutions afterwards, I find it not to be ideal either, because sometimes you people have bugs, and as much as I like coding and I'm used to coding, catching other people's bugs is not easy, let alone in languages I do not code in, such as R and MATLAB. So I most likely will not be catching your bugs. So halfway through the lab, I will release the solution, so that if you are stuck because of some stupid typo somewhere in the code, you can catch it up yourselves. Okay? So let's see if I find the handout, first of all. Hopefully I do. So did you find it?
Is it this one?
It's yeah, it's that one. Yes, there's 3 versions. And I will be showing what I mean by I will not release the solutions is that I will not upload the solution, but I will be showing you the solution after each of the assignments. So I will go through the solution with you here today. Okay? So let me know when you have it, and I'll start going through it a little bit. So basically, we are gonna see in practice what we discussed the past 2 days, starting with the hawk and dove game, and we will be implementing this game. So I assume you've already coded up differential equations, right? So you know how to integrate differential equations on a computer. That's good. So essentially, okay, you have it in the handout, but so you have it here as well. We have our payoff matrix, okay? Sorry, the HD that we saw yesterday, all right? This is a 0, this is a G, and this is a G over 2, okay? So essentially, these are the parameters of our model. Therefore, I will ask you to draw the analogy between the payoff matrix and the replicator dynamics governing the time evolution of the system. So essentially, you will have to code up the differential equation corresponding to the replicator dynamics given the payoff matrix. So your parameter of the model is the payoff matrix, okay? So there is a little bit of a recap to start with. I mean, you can choose how much, depending on how much you remember what to take out of this. But essentially, we will be writing again the payoffs for the hawks and the doves. And then from these, you have that the fraction of hawks, as we saw yesterday, is given by x times 1 minus x times ph minus pd, okay? This we saw yesterday. And you have it as a function of the parameters in the handout. So here, so depending on what language you use, what integrator you decide to use, usually when you integrate ODEs, you pass a function that takes the state of the system and returns the time derivatives, right? This is what most of explicit integrators do, okay? This is not a stiff system, so there is no need to use implicit numerical integration. So you will be coding up a function that looks like this one and takes the state of the system, and there's a function of some parameters that, for instance, in Python you can pass as a dictionary or equivalent data structure in whatever programming language you code in. It will return the derivative, right? And then you will pass it. You can either code up your own Euler integration scheme or Runge-Kutta or whatever you want to code up, or you can use some library that does that for you. It's up to you what you prefer. So the other thing I would like to make clear before you start coding is that this is not an exam, okay? So you are more than welcome to group together and solve these in groups. I mean, or you're also more than welcome to do it on your own, but it's up to you. Don't take this as a test. It's not. It's a lab. So given this snippet that is basically going to be the core of the first part of this lab, where we will be integrating deterministic differential equations, you are given another snippet that you need to complete each task. And in this case, the task is to try and simulate, for given a certain gain parameter, for 3 different values of the cost parameter, to integrate the system given an initial condition and see what the dynamics are, okay? So this is essentially the first problem. So I will let you try to do it. Take your time to set up. So this is going to be about 1 hour and 20 minute lab. There's plenty of time, so feel free to take a little bit of time to set up your working station and get your workflow ready. So I will be giving you a little bit more time for this first problem. Yes?
We have basically the same version that you have which seems to be already all the answers.
Really?
Like these functions are on our...
So let me just double check real quick if I do have the thing. So, Okay, so yes, thank you for pointing that out. I inadvertently had uploaded some of the solutions already. These are the three handouts that I'm referring to. Okay, the one where there is written student. And for instance, if you take the Python one, there are some snippets, okay, like this, but you need to complete. I mean, it's not like you have to write a ton of code, which is why maybe it's better that you don't copy paste this from this PDF and you actually write it. But you need to fill in some parts to complete this, okay? And then in the solution, there's going to be the whole code and the plots you're supposed to produce. Which, okay, in this case, the plot is already here, but still you need to do it yourself.
Okay, there's parts of
Yeah, you need to fill in some parts, okay? And the other thing, today, so this lab has 4 parts. Today we will be doing the first 3 parts, whereas the 4th part, we will be doing it next week together with the collective behavior lab. So if you're fast at coding and you're done with the first 3 parts in advance, do not do the 4th part. Tell me, and I will do it. I will give you some other thing to do instead. Okay?
I forgot my key, so I'm going to get one with Natalia because my computer is locked.
Okay, no worries. So if you have doubts or you're confused about either the question or the methods, don't hesitate to ask, okay? So by the way, that's the same folder where you have the material of the course, okay? Just in case you hadn't found it yet. So how are we doing? Who finished the first one already? No one? Eh? The first the first that is called challenge problem, whole kind of game. The three differences. Sorry? Okay, great. So when I'm talking about problems, I'm talking about this grayed out box, let's say. So those are the things that I refer to as problems or exercises. Okay. And the text is essentially a recap of what we did yesterday. Yeah, maybe it's not super clear. So is anyone having some problems with this? Is it all good? Great. Yes.
Right here, when you define the code, you're calling parse as a dictionary.
Yeah.
But here, when you use it, you pass it as a tuple, and A is just an array. So, isn't there going to be a problem?
So this is the first part is a pseudocode. So this is meant to mean that, right?
I get it.
Yeah. So I mean, the exact implementation you choose what you're more comfortable. Essentially, I mean, it actually also depends on what integrator you're using, because some integrators require certain syntax and then different syntaxes than others, right? So in the end, your code needs to run and needs to do what it needs to do, but the exact implementation, it's up to you. There are many different solutions to the problem. So just as a clarification, since other people may be wondering the same, so these snippets, they tell you the logic. This is pseudocode, okay? You don't need to copy paste stuff from here. You need to also, essentially, what you need to do is to solve the problem that you're given, and how you decide to implement it. The details, whether you pass a dictionary, whether you pass a tuple, whether you pass a list, is up to you, okay? I'm not here to tell you that you should pass dictionaries instead of tuples. I don't care. Like, you do what you feel like more comfortable doing. Okay.
So the figure should behave exactly as it is on the board, right?
Yes, technically yes. Unless, well, let me actually double check my code, because sometimes there have been several versions of this. Yes, this should be the figure. Yes.
Is that correct? I mean, I'm supposed to fill this value
Yes.
in here.
Yes. Like, this is MATLAB? What is this? R?
R.
R.
And then I see the bar row, and it's
Yeah.
filled by row.
So, yes, essentially the parameter is, then I don't know how R passes things to the integrator, but the parameter is essentially the matrix. What you may need to double check is that you're actually not transposing it by mistake. Okay, that the value I 0 1 1 1 1 0 1 1 1 0 0, sorry, are the ones that you expect. Yeah, sure.
So we have to do A, B, and C.
What's A, B, and C? What are you referring to?
The sections. This one.
Yes, yes, but yes, you can go ahead if you want, but I will go through the solution of A first. But yeah, you can go ahead and do B and C as well if you're done with A. So who's already done with section A, with the problem of section A? Okay. So I will wait a couple more minutes for other people to finish as well, and then I'll give you the solution. So in my own experience, either the problems that emerge with this kind of code are either integration problem because of the syntax of the integrator you use, or sometimes the one mistake that can happen while you code it up is that you essentially transpose the matrix without realizing it. That you put some values in the metric structure and then the code reads it as the transpose of it, and therefore what should be the payoff of a hawk against a dove ends up being the payoff of a dove against a hawk. So these are the two kind of mistakes that people usually make when solving these type of problems. So who is stuck? Who feels stuck right now?
Well, we're just trying to figure out exactly what each term means, but okay, here it's R1, right?
Yes, that's right.
So in the pseudocode that you pass to us, you use the first, the element that is the first line in column of the array.
Correct.
Which needs to be, where is it? This, right?
Correct, yes. Well, okay, so this is an extensive notation where the first entry of this tuple is the payoff to the player 1 in this interaction, and the second is the payoff to the player 2. But you will notice that this is symmetric, okay? So I actually simplified the notation like that when I was teaching you this. So perhaps it's easier if you think about that matrix rather than thinking about this matrix, because it's not you don't need to give a tuple here. It's just G minus C over 2, G 0, G over 2.
Okay, so there's the first element of the tuple.
Exactly.
Yeah, but it's still in my mind to define R1 we need to use just okay. We need to use just G, right? And here we will be passing G.
No, but this is Pioch either this is the result of this. Therefore, this is the payoff of the hawk, either facing another hawk or facing another dove. Whereas what you were talking about was the entry when a hawk faces a hawk. Okay. So if you look at the pseudocode.
Sure.
If you look at the pseudocode, then the function essentially writes down that equation, right? So x times matrix 0, 0 is the payoff of a hawk against a hawk.
Yeah.
Okay?
Okay.
Plus 1 minus x, the matrix 0, 1 is the hawk against a dove, right? Yeah, okay, so that's... So something that might be a little implicit, so I will clarify that for everyone, is that this is the replicator equation, And these pH and PD are written in terms of the matrix entries, okay? So if the matrix has entries PHH, right, the usual notation for the denoting matrix indices, PhD, PDH, PDD, the payoff of the Hawk, which is this one you have in the equation, is going to be X times PHH plus 1 minus X PhD, right? So it's not, you don't need to solve the algebra to write it in the function. You just give the matrix to the problem and the function will know what entry of the matrix correspond to what term in this equation, okay? So this is essentially what this snippet is doing, the pseudocode of that snippet is doing, okay? And same thing for the Dove one, right? PD is going to be X times PDH plus 1 minus X PDD, right? Sure. Hey.
More Python, okay? That's okay?
Yeah. You can do whatever you feel like.
Alright, so I took the code here. I'm reading still what this code do.
It's yeah, okay. It was division for like in there is a difference between Python 2 and Python 3. In Python 3, when you divide two integers, it gives you a float, whereas in Python 2, the default behavior is that when you divide two integers, it casts the result to an int, so you get the integer part of the result. And this is basically telling your code, even though you don't need it because you're using your kernel is running in Python 3, so you actually don't. This line of code doesn't do anything for you.
Ah, okay.
Yes. Yeah. Okay.
My question is, I set I got what we're doing here, but I had an error in the syntax because I'm not found where I put part here, because I already put the matrix here, but I'm not seeing how do I mix these two codes.
So, first of all, now you have a syntax problem.
Yeah.
Right? So what you did is that you defined a function that takes some parameters,
Yes.
but you didn't specify what those parameters are, right? So now you just defined a function that returns a value, and you're gonna have to pass this function to, like you're doing, to the integrator, okay? But you need to initialize the problem as well. You didn't tell anywhere in the code what parse is, and also, the other thing is in the handout, if you go to the snippet.
Sorry?
Right, so this is a pseudocode that tells that you need to take some parameters and give it to the function, and in this case the parameters is essentially it's just the matrix, but in the snippet now it's giving another syntax which is passing a tuple of A and G, okay? So you can, the two things are incompatible. The point is you need to tell your function needs to know what it has to do, essentially. Whatever you decide, whichever implementation you decide.
Okay.
So if you go back to your code, first of all, you're not initializing, like, you're not giving initial conditions, so you're not specifying any of this, right? The code doesn't know what A is, what G is, Okay.
I did. First of all, I did this.
You did it afterwards.
Yeah, and then I saw that this came first. So
Okay.
I thought, oh man, I need to change. But actually, I need
No,
to
you-
set this first, and then this.
So the exact implementation of the code, it's not the point. The point is that you take the task and you get from a point A to a point B using coding. Then how you choose to implement it is entirely up to you. I mean, you don't have to.
Doesn't care.
Yes,
Like,
exactly.
Doesn't care about it.
Exactly. But so here you defined your parameters, and now you can try to do something like this. But you need to say to the code what parse is, right?
And that's my my question. What parse is?
Parse, you could either write it as a dictionary. For instance, you could say parse equal to open close brackets for the dictionary, like the special brackets for the dictionary. Graph, I don't know how to call that in English, but this one here, the one on the top.
Okay, it's here it's Chaves keys.
Okay. and then you tell the code parse A with the key A equal to your matrix A, for instance, but not inside the function. Here, when you initialize the problem.
Here.
Yes. Yes. Well, first you need to so have you ever used dictionaries in Python?
Yeah, I'm starting on it.
Okay.
That's why I'm trying to.
Okay. So you need to first you do something like okay. How do I do this on this computer?
Shift.
Okay. And then you do something like, how do I do the other bracket here? Like this, okay. And where is the thing to write A inside? Yeah, but it's a string. Yeah, there you go. And then you say A, for instance, right? Yes. So you see? Okay. No worries. So it takes a little bit of time to get used to it, but sure.
Professor, é pra gente fazer a parte 3 estocástica ou não?
We are, it's okay. We are going. Wait a little bit for the stochastic part. I would like to give you some theoretical notion first. I was wondering whether you were talking to me or. Okay, so everyone, I'm going to go through a little bit the solution of the first problem. Okay, so essentially. Again, the precise implementation doesn't matter, but how I chose to implement it was through a dictionary where I give the matrix as a parameter, okay? This is just the matrix that I wrote there, all right? This doesn't really matter for now, but, and then you create a list of the different C's that you need to cycle on, right? Because the problem is asking you to try three different C's. So one possible way to do it is to write a list of the parameters that you need to try, and then you cycle over it, okay? And you redefine the entry of the matrix based on the new parameters for each of the C's, right? And then you integrate these passing. In my case, I decided to pass parameters as a dictionary, so I would do something like this, okay? In the snippet, it's passing it as a tuple. I mean, you can choose whatever you prefer to do it, whether you want to encapsulate everything in a dictionary or whether you want to have a tuple with the different parameters. So, and then, okay, you integrate it and you plot it, and you should get something like this. So basically, this is showing that no matter the value for C, as long as C is less than G, okay, G is 10 and the maximum C here is 9, eventually, after a certain amount of time, the population will be dominated by hawks, right? Which is what we saw yesterday, right? Yesterday I showed you this diagram where when C is smaller than G, if this is the phase diagram, you have 1 and 0, and the fixed point is x equal to 1. So this is what we are seeing with this code, okay? Yes.
So I'm more used to R, but since we are learning Python the last discipline, I tried to do it in Python first, but something is not right. It says HD model takes 3 positional arguments.
Yes.
5 are given.
Go up. So
Okay, so here,
what are you using? What integrator are you using?
what are we doing?
ODINT. So you need to write something like args equal. Also, what is your parse? What is you define parse? But you need to do it afterwards, right? Ah, I see what's going on,
I
actually.
need to do it here?
Yes. And this is not a dictionary. So if you want to use this syntax, you should pass a dictionary. So
Which?
So
We
this is a
we
tuple.
actually haven't learned what is a dictionary.
I
It
see.
stops in arrays.
I see. Okay.
List,
I
arrays,
see.
matrix, but not dictionary. Tuple, I don't know what it is either.
Okay. So if you don't know what a dictionary is, maybe the easiest thing is just to write something like you just write A as an array and you pass that. And now the function, you need to change it, right? So the function will be something like, so let me do it in a way. You will pass directly A, for instance, okay? And then instead of parse A, you will have A, right? For instance, you could do something like that. So you don't have to pass you don't have to use a dictionary. I mean, you can use, if you only know arrays, you can just use an array, right? Something like this, no? And then instead of passing the parse here, args equal to parse, then you would say args equal to A. But yeah, so dictionaries are very useful. So if you want to use Python, you should learn to use them. Yeah. Yes.
Said for us to modify the loop, but there is no loop up here. But I don't know if it's what it means.
So the loop, the problem B is referring to the loop you needed to write for the problem A. Because you had to write a loop for the three different C's.
Yes, I have made
Oh,
it
this
for.
this is another C.
just-
Okay, nice. Right, and now the other problem is asking you to cycle over initial conditions. So in the loop, instead of cycling over C, you cycle over the initial conditions.
Okay, thank you.
Sure. Okay, so for people that want to use a dictionary for the first time, if you want to try, you can define a dictionary in several ways. One possible way is that you define an empty dictionary with these, I don't know how to call them in English, but it's these brackets. These are the brackets that define dictionaries in Python. And then you populate your dictionary as if it was a list where the key are strings, basically, if you want. You could think about something about it like that, okay? And then you tell to the dictionary, look, the dictionary that corresponds to key A, it's this thing. And then you can use this dictionary, for instance, inside the function. And this is useful, for instance, when here the parameter is only the matrix, but you can have other more complicated situations in which you have many different parameters that do many different things. And instead of passing a list and having to remember the number 3 of the list was this parameter, the number 5 of the list was this other parameter, where if you start having 10, 15, 20 parameters, then it becomes a bit of a problem. The dictionary takes strings as key, so you know that the string that you call a certain way corresponds to that parameter. So this becomes very useful when you have many parameters. With one parameter, it doesn't really matter. Yes? I cannot really read. Okay. So then the question is whether that's the right matrix.
Yeah, because when I got this,
What do you get as a result?
it's error here. But I don't know if this is correct. Like the way that I output.
Well, this looks like a syntax error. I don't know R, so I cannot tell you what is the error. But this looks like you wrote, maybe you add one more parenthesis that you need. Are you closing two parentheses when you open 3? It looks like, no?
Yeah.
Something like that, no? Or maybe there is a symbol the thing doesn't know. But the matrix is the correct one, but there is a syntax error there. Okay, so I hope you get more or less the idea. So if you want, you can continue doing, so problem 2 basically, the second problem, basically tells you to redo essentially the same thing with the other value for C, that is now is bigger than G, to check that no matter the initial condition, when C is bigger than G, you get to a fixed point that it's mixed. It's not the hoax dominating anymore. Okay? So essentially, in problem 2, you need to get something like this so that you see what we saw in the lecture when C is bigger than G. You get a fixed point that is in the middle, okay? So you can go ahead and do it, but now I would actually like to think about stochasticity for just a little bit. So if you want, you can ignore this part altogether. It doesn't matter. But for those that want to try to do it, I would actually like for you to try and go through, to even maybe skip the problem B, and to try and go to section 3 where we do some stochastic processes, okay? because everything you did so far is deterministic. So it would probably be nice for those who want to try and do some stochastic simulations. So in the end, who doesn't want, it doesn't matter. I mean, you can just keep doing the deterministic stuff, but I would like to give a little introduction to the stochastic thing for the others. So basically, I told you that these payoff entries can be thought as rates, right? When we think about them as fitnesses, fitness as unit one over time. So essentially, these are rates, okay? So this means that the payoff, for instance, if you have a hawk against a hawk, it will have a payoff HH, as we defined it before, which is going to be equal to G minus C over 2, okay? If this is bigger than 0, then this is you can think of it as a birth rate, okay? If this is smaller than 0, then the modulo of it, the absolute value, sorry, is a death rate. Okay? Meaning it's the rate at which hawks will die in your simulation. And the same thing goes for those. When you have some payoffs that are positive of its birth, which in fact in this model is the only thing you have for those, and when it's negative, you have death, okay? So if we realize this, we could try to implement a stochastic version of this code where, given the interaction between the pairs, you have either stochastic birth and death dynamics. And what I mean by it is that imagine that so the pseudocode could go as follows. So you would loop over time, and at each iteration of this loop, you would increase by a fixed amount of delta t, essentially. So you keep the delta t of the integration fixed, and you loop over the time until you reach TF, which is whatever simulation time you want to achieve. Then you cycle through, and this is the part that sometimes is a bit counterintuitive. You basically cycle through n random games. What this means is that for each of these n games, and n can be interpreted as the population size, okay? So if you want, whatever we did so far is in the limit of infinite population. Everything was deterministic, and we were studying a continuous model for the frequencies, which means that you're sending a population size to infinity. But if the population size is finite, and you have a stochastic process, then n is the population size of the system. And basically, for each of these n random games, what you will do is that you will choose two players at random. So for instance, player 1 will be a hawk with probability x, right? because in your system you have x is the fraction of Hawks. Therefore, the probability if you draw a sample from it, the probability that you draw a hawk is x, right? Or it can be a dove with probability 1 minus x, okay? And the same goes for player 2. So you draw player 1, you draw player 2 with the same rule, assuming you don't care about repeating the same draw as before. So if you want, for people that already have some modeling experience, this is making the assumption that the system is mean field with respect to whom I'm drawing. This is a mean field assumption. You're not keeping track who you drew before drawing the next player, okay? Once you have these two, basically you have you can evaluate the payoff given the player 1 and the player 2 that you drew, okay? So you have the matrix there. That gives you the payoff. Now, if the payoff given player 1 and player 2 is bigger than 0, this is a birth rate, as we said before. If it's smaller than 0, it's death, okay? Okay? By P12, I actually mean okay, I'm abusing notation a little bit, but I actually mean P1, P2, okay? All right? So, what is the thing here? It's all written in the PDF, but I just wanted to give you a little bit of the idea on the blackboard as well. Now, once you know what the payoff is and whether that's positive or negative, that gives you the rate, right? Either be it the actual payoff or the absolute value of it if that's less than 0. Therefore, you will assume that this is, who has seen Poisson processes before? Everyone. Okay, good. So, if you have a Poisson, you're going to assume that these processes are Poisson processes?
Actually, did we? I think we just saw the Poisson distribution.
Ah, okay. So, essentially a Poisson process with rate lambda is a process that is defined as a memoryless process where at each infinitesimal time you have a probability lambda dt of an event happening. This is the definition of a Poisson process. You can derive mathematically a number of properties of these processes, one of which is that the probability of an event, of having an event in a time delta t is indeed the Poisson distribution that you saw, which is given by lambda delta t to the power n over n factorial e to the minus lambda delta t, okay? And the other very important property of a Poisson process is that the interarrival times are exponentially distributed. So the time between event 1 and event 2, where in fact the time between event I and event I plus 1 is distributed and I always mess up the normalization here, but it's distributed as e to the minus lambda, so the probability of this, e to the minus lambda t, and this should be lambda, I think, or 1 over lambda. So, yes.
Wait, just a second. The probability for time going from time I to I plus 1?
No, I are events here. The interarrival time probability, the interarrival time probability between consecutive events is exponentially distributed. This is a super important property of Poisson processes. And so why is this important? Because actually this implies a way to implement Poisson processes on a computer, which is called Gillespie algorithm, where basically you draw interarrival time exponentially distributed one to the next. So this is actually not a Gillespie algorithm, so I will not tell you the theory behind it. I actually thought you had done some of this already, but essentially, if it's true that this process is Poisson, the Gillespie algorithm is the correct way to implement a Poisson process with different rates. The problem with the Gillespie algorithm is that the time complexity scales linearly with the number of the rates that you have in your system. And if n becomes very big, so if you have many games, this becomes too big. And therefore the big Gillespie algorithm becomes too slow. So you need some approximation. And actually what I was going to present you today is the approximation. But it's good that you know that the Gillespie algorithm exists. So I mean, at some point you will learn about it a bit more thoroughly. So, but okay, stick with me for one more second. So let's say that the probability of having any event in delta t is given by this Poisson distribution. Now, the probability of having one event in delta t is going to be given by lambda delta t times e to the minus lambda delta t. And if you're careful and you make a good approximation, meaning delta t becomes small, you can just Taylor expand this and you get this is equal to lambda delta t plus stuff that are of the order of lambda delta t squared or smaller. And therefore, since you're making the approximation of lambda delta t going to 0, the probability of having one event is just lambda times delta t, okay? Therefore, given delta t that is fixed, and given your rate lambda, that is your payoff matrix, you can calculate the probability of drawing one event in a delta t time, okay? And what does this mean for us? This means that you will draw, given by this, you will draw if birth or death happens. So this approximation, again, as you can see, it's only valid in this case when lambda delta t tends to 0, which is why this is an approximated method to integrate stochastic systems. And this is called Tau-Lip algorithm. Whereas if you were to simulate the whole Gillespie method, you would just draw inter-arrival time, and then you would draw which of the rates that corresponds to. I know it's a bit abstract if you've never seen this, but I don't really have time to go through the Gillespie algorithm right now. Yes.
So with this, we're assuming that sorry.
So in this case, we're assuming that the delta t is small enough so that the probability of drawing more than one event is basically zero.
Essentially, yes.
Okay.
Because this basically makes the assumption, the underlying assumption of this. You know that who you draw, drawing an H or a D depends on the state of the system. And now, based on whether you drew a birth or a death, you will update the state of the system. So if you have many events during the same delta t, this is incorrect because you're not updating the state of the system before drawing all of these events, essentially. And so this makes a mistake in the numerical integration, which is why you need to pick a delta t that is small enough. Yes.
So just so we can go through this together.
Yes.
So we're going to have an algorithm that plays n games in delta t, in a small amount of time.
Correct.
And that's the typical time that it takes for the interaction to occur.
Right.
Then if the payoff is positive, we add a birth to the player 1.
You need to draw.
Okay.
If the payoff is positive, you draw whether you do have a birth or not.
Oh, okay. And the draw probability is proportional to the rate times delta t.
That's correct.
And how do we define the rate again?
Lambda is equal to P1, P2, if P1, P2 is bigger than 0. So it's basically the absolute value of P1, P2. Where if this is if PP1, P2 is negative, that's a death, and if PP1, P2 is positive, it's a birth. So you actually need to keep track whether this is positive or negative, because then, and let me actually finish the algorithm because yes. So if you draw a birth, say that for instance you draw a birth of a hawk. Then you need to draw a third player. And I know it's confusing, but for now, trust me. You need to draw a player 3. Actually, you need to draw it anyway, so you do it first. So, with the same probabilities. With the same probabilities, right? The point of drawing the third player is that if you have a birth or a death event, this third player is going to be the one that gets substituted in the population, either by player 1 if it's born, or it will substitute player 1 if it's dying. Because we are keeping the population size fixed. And I'll try to explain why is that in 1 second. But for now, just trust me that this is the correct way of simulating this process. So you draw P3. Therefore, if player 1 is a hawk and it's born, and P3 is a dove, because if P3 is a hawk, nothing changes because you either replace an hawk with a hawk, well, you replace a hawk with an hawk either way, whether it's born or it's dying. So the population composition doesn't change. So if P3 is a dove, and you have a birth of a hawk, x becomes equal to x plus 1 over n, because n is the population size. So you drew one more hawk. If h dies, and again P3 is a dove, then x is going to be equal to x minus 1 over n, okay? Because you're replacing a hawk with a dove, okay? You don't use player 2 to do this replacement. You use player 3. And I will tell you why in just a second. So you update this, and then of course you finish the loop over, okay, and then of course you also have the case where player 1 is a dove, which is just the counterpart of this, right? So after you loop over n finishes, you update the time, and you go on until you reach the end of the simulation, okay? So there are a couple of things that are counterintuitive in this. The first one is that you need to cycle through n games. And essentially what this is doing is, if you want, this is something like, who knows what a Monte Carlo algorithm here is? Okay. So this is a random sampling algorithm. So you're sampling at random some player in the population. For this is essentially equivalent to do a Monte Carlo over the population, for those who know what that means. And if you don't, it doesn't matter. You do it just to sample the whole population, essentially. And then player 3, you need to draw it instead of using player 2 as the one that replaces or is replaced. Because if you use player 2, you will introduce in the system some correlations that will make it so this process that you are simulating is not equivalent to the replicator dynamics that we were studying in the deterministic system. And this can actually be proven mathematically. So I don't know if I have, I have 5 more minutes. So actually, if you want, so the structure of these labs is quite flexible. So if you want, we can actually continue this together with the other stuff in the next lab that we will have next week. That you can discuss it among yourself, and you can let me know already directly next week whether you want to do it or not, okay? You don't have to decide now. But just to give you an idea of what I'm talking about, basically, you have a rate process. Have you done stochastic processes before? In this course. Okay. Okay. All right. I'll try to give you a little bit of the intuition. So when you have some rates, you either have a rate of a hawk becoming 2 hawk if it's a birth event, or a hawk becoming nothing if it dies, okay? This is the same way you write down chemical reactions if you want. If you want the Gillespie algorithm and the Taolit algorithm were originally proposed by Gillespie to integrate numerically chemical reactions. And then this was transposed to stochastic models of other parts of biology too, because it's very powerful. So this birth event, consider the case, for instance, where the cost is bigger than the gain. Therefore, when hawks interact with hawks, they die, and they are not born. I'm just, what I'm telling you is general. It's general with respect to this assumption, but just for making an example which is a bit simpler, I'm gonna assume this for now. The rate goes as x times y minus x squared times g, and this means that you drew a hawk as player 2. And then you drew a dove as player 1 and player 3. Sorry, this is not true. Is this wrong? Wait a second. No, this is right. So actually, you draw a hawk as player 1. You draw a dove as player 2 and as player 3. And the payoff of a hawk given a dove, it's G, okay? So you have a birth rate G times the probability that the player 1, the focal player, is a hawk, that the second player is a dove, because this is the second player, and you're replacing a dove. Because again, if you're replacing another hawk, the population doesn't change, okay? Plus 1 minus x times x squared times 0, because this is the payoff of goes to a dove if you draw a hawk. This would be the case if you drew a dove as player 1 and a hawk as player 2 and player 3. Okay? Nothing happens in this case because the matrix entry is 0, but there are other cases in which this might not be true. Okay, so you always need to consider all possibilities. And then the death, you just need to consider G minus C over 2. So in the case a hawk kill another hawk. So you have x squared because both P1 and P2 are hawks, and 1 minus x because P3 needs to be a dove, okay? Plus the probability that player 1 and 2 are doves and they replace a hawk. So you have 1 minus x squared times x times g over 2. Now, if you sum all of this together to write down from this rate, you can write down the deterministic part of the time evolution of the composition of the population. You essentially do this minus this, okay? Because in this case you have a birth, so the state goes from n to n plus 1. In the other case, it goes from n plus 1 to n if you have a death. So when you do the finite differences, you take this rate minus this rate. And if you write it down, you get and you factorize this all x times y minus x's that you have there, you will get 1 minus x PhD minus x modulo of g minus c over 2 minus 1 minus x PDD, okay? And therefore, since this is negative, you have this. And this is exactly the replicator dynamics that we were studying. So if you want, this is a way, and there is a more general way to prove it without assuming this, okay? So this is a way to prove that these stochastic processes that I gave you, on average, gives the same deterministic model that we were studying before. I know I went very fast, so it's totally fine if you're confused. But I just wanted to give you a little bit of the idea behind two things: how to simulate a stochastic process. Also, what a stochastic process is if you never saw one before. Essentially, it's an instance where at each time point you draw some random variable, you draw a coin or a dice. This is certainly not the simplest way to see stochastic processes for the first time, but and then the other thing I wanted to tell you a little bit was how to connect a chemical process or a rate process given some rates to the deterministic equation that governs the average dynamics, let's say. So this was more or less the idea that I wanted to give you. And I will give you all of the solution to this thing, to this lab. You can decide what to do with it. Like if you want to try it, if you want to explore it a little bit. In case you want to do it on your own and you have questions, feel free to reach out either by email, by Slack, or you can also just come to my office 109 and ask me some questions, either on the coding or on the theory as well if you want. And again, next week labs take a bit of both game theory and collective behavior. So if you decide collectively all together that you want to do a little bit more of this, we can do it. Otherwise, I will go on with the other stuff. You let me know on Monday. Yes.
I just wanted to correct what I said before, that we didn't have seen stochastic processes, but we did see Markov chain. So
you saw Markov chains.
Yeah, a bit,
okay.
Just a bit, I think.
Okay.
Yeah.
Okay. So if you want, these actually can be formalized as a Markov chain as well. So, but it's a bit involved because basically the state now is the number of hawks and doves, and you can write down the master equation. Did you see master equations with Markov chains? No, you didn't see the master equation. Okay, so you only saw discrete matrix transitions. Okay, I see. Okay, okay, that's fine. Okay, so again, I will upload everything, and then you let me know how much you want to, continue with this topic. All right, thank you.